folks, welcome back. So let's try and formalize a little bit more how you go from a rational exponent like a to the m over n to a radical, right? So how do we convert between radical and rational exponent? And we've touched on it a little bit, but I want to formalize it. So when you have a to the m over n, there are two radical expressions that you can swap this into, that you can convert into, and they're equivalent. So what you could do is whatever this, I'll start with the denominator. The denominator is always going to be the index. So you can you can see in each form, right, you have the nth root. And it's up to you when you want to use the nth power, right? So this n, the denominator will always be the index in both radical expressions. And it's going to be a matter of if you want to do the nth root first and then take the nth power, or if you want to take the nth power first and then take the nth root. So here with the numerator, you're always attaching that as the power, right? So if you look, you can do a to the m and then take the nth root, or you can take the nth root and still raise it to the nth power. So somehow you're raising something to the nth power, and somehow you're always taking an nth root. So in words, you can raise a to the mth power, so I can do a to the m, and then I can take the nth root, or you can take the nth root first and then raise it to the m. I typically do this one first, or this version. I take the nth root, because a lot of times when you take a root, you make a number smaller, and I like to deal with smaller numbers. So I'll make the number smaller and then I'll make it bigger. In this version, you make it bigger, right, by taking a to the m, and then you make it smaller. So I just find, especially if I'm using my brain calculator, like this is simpler for me. Again, not saying it's easy, or I should say easier. It's easier. I'm not saying it's simple. All right, so let's practice some of these. So we're going to write each exponential as a radical, right? I've got all of these exponentials. We're going to assume all variables are positive, right? So we don't have to worry about domain issues. All right, and we're gonna do the version that takes the root first. So I'm gonna do this version because, like I said, I like to take the root first and then raise it. So now this is 19 to the 1/2. So what that essentially means is I'm going to take the square root first, right? There's the 2. And then in theory, I would take this to the first power. All right, so your denominator becomes your index, your numerator becomes your power. All right, now in this case, the power is 1, so it's nicer, right? I don't have to worry about it. So this ultimately is just the square root of 19. There's no way for me to simplify this because 19 is prime. It doesn't have any perfect squares in it. All right, so let's think about 5 to the 2/3. All right, so I'm going to handle the radical first. So I'm going to say this is the cube root of 5, and then I'm going to square it, right? So the the denominator becomes the index. This numerator becomes your power, all right? So I'm going to write this as the cube root of 5 quantity squared. If you wanted to do this version, right? If you wanted to, right? But let me back this up. Cube root of 5 is going to be a pretty small number, and then I can square it. The other thing you could have done, if you want to do this representation, is you could have done the cube root of 5 squared. All right, so as long as you have that power somewhere, either on the radicand or outside the radical term, you're good to go. All right, so we want to be careful with C, because this is not 4k in parentheses to the 3/5. This is 4 times k to the 3/5. So really what's happening here is this is 4 times k to the 3/5. So I'm going to work on that radical term first, and then I will multiply it by 4. That's very different than if I had 4k to the 3/5, where I'd have to have 4 in this 3/5 exponent as well. But this is just 4 to the 1, right? 4 by itself and then k to the 3/5. All right, so we're going to take the root first. So I'm going to use that denominator. So I will have 4, and I'm just going to put times right now. This is going to be the 5th root of k, and then I'm going to cube it. All right, so I'm taking that root first, right? And then I've got my radicand of k, and then I'm going to cube it. If you wanted to use the other form, which again, it's not my fave, but you could say this is 4 times the 5th root of k cubed. All right, so you could do the power first, right, and then the nth root of it. right? Or I should say you could cube k first and then take the fifth root. I think it's simpler, especially when you're working with numbers, to take the root first and then do the power, okay? All right, so let's scooch this up and see if we can't make this work for some trickier expressions, okay? So if I look at this one, right? Now I want you to take note, here, there's not parentheses around the 5x, here there is, right? So in this first term, it's only x being raised to the 3/5. The 5 is not, it's just a multiplier, right? Here the 2x, the entire expression, because it's protected with those parentheses, is being raised to the 3/5. So this 5 is going to become the index, right, when I make my radical, and these 3's are going to become my power. So I'm going to have 5 here times the 5th root of x, all of that's going to be cubed, right? So the 5 is, this 5 is that multiplier, this 5 in the denominator is my index, and 3 is the power, okay? And I'm going to subtract out, I've got no multiplier out in front, right? I had a 5 here, but the 2 in the 2x is in parentheses, so that's all going to become the radicand. So my 5 is the index, and I'm going to have 2x here. Oops, I don't need to put that in parentheses. Let me erase that. My bad. I was thinking of doing it a second way, but I won't even go into that. So I'm going to have this 2x here, and then I'm going to cube it, right? So that's how we can do that. So again, taking note that just the x had the exponent of 3/5, that's why it became the radicand. Here the 2x collectively, right, because of that parentheses was being raised to the 3/5 power, that's why the 2x is in the radicand. And if you wanted to write it the other way, right, just to show you an equivalent way, you could do, this could be 5 times the 5th root of x cubed minus the 5th root of 2x cubed, right? So that's a different way to write it, where you do the power first and then take the root. I tend to take the root first and then do the power. All right, so if I look at e, I see that negative exponent. So the first thing I'm going to do is travel it. This is going to be 1 over x to the 5/7. So once I've traveled it, I'm good to go. And let's rewrite this term as a radical, right? So if I want to rewrite this as a radical, this is going to be, I'm going to have the 7th root, my radicand x, and I'm going to raise it to the 5th power. Okay. Now, if you wanted to, it's up to you. You could have done 1 over, oops, excuse me, I have an appointment coming, 7th root of x to the 5th. So you can either put that exponent or that power inside the radicand or outside. I tend to do it this way. All right, I wanna talk about this one. All right, so I get this all the time, that students want to distribute this 1/3 to this binomial. And I say binomial because you have m cubed as a term and n cubed as a term. You have two terms separated by an addition symbol, right? Two terms. This is a binomial, and you cannot distribute exponents over addition or subtraction, right? So I get it all the time that students will tell me, oh, this is m cubed to the 1/3 plus n cubed to the 1/3. And then they'll multiply these exponents and they'll tell me this is m plus n. This is not true. I want to make sure we're clear here. You cannot distribute exponents over addition or subtraction, right? You can't distribute them to binomials, trinomials, you name it. So I'm going to write this, we cannot distribute exponents over addition and subtraction. You can distribute exponents over multiplication and division, but you are not allowed to do it if there's a plus sign or a minus sign here. So as soon as I had a binomial, I can't distribute. What I can do is treat this, because I need to get it into radical form. Well, if I see that 3, let me scooch this up just a bit so I have a little bit more space. If I see that 3 in the denominator, that is a cube root, and then I can write m cubed plus n cubed here. But that's all you can do. Again, I want to be super clear. You cannot distribute this exponent over this addition. And just as a side note, I'm going to put a little separation bar here. If you had something like this, if you had m cubed, n cubed, to the 1/3, right? If these two terms, these two nomes, it's not a binomial anymore, it's just one term. If they were separated by multiplication, then you can distribute the exponent. So that rule is fine. But if they're separated by a plus or a minus sign, you're done. You cannot distribute it. All right? Thanks so much. Bye.